So the plan for today is to focus on the whys and what's behind EVPN. So heavy on the theory. We'll take a break halfway through, and towards the end, hopefully we'll have time to get on the CLI and run through an example. The lab, I don't know if any of you guys have had a chance to take a look at it. It's going to build upon the VXLAN lab. So if you have completed the VXLAN routing lab, you will be able to clone that, and you won't have to worry about your underlay or your VXLAN overlay. So that would be good. And then you can just focus on EVPN. If not, then it'll just be a little bit more legwork, but that only makes you stronger in the end. As you have questions, don't hesitate to interrupt and ask for clarity. Or for those of you who are on this for a refresher, if you've happened to run across a case or something else and you would like to share a story or some context, please do. With our theory today, we're going to talk about, well, EVPN internals, and there's lots of internals, so that'll be fun. Some design concepts, and then layer 2 VPN as a service. So you'll notice in the lab, there will be no layer 3 as far as EVPN goes. We're gonna do pure layer 2 to start. All right, so what is the reason we have EVPN in the first place? Well, EVPN or Ethernet VPN has actually been around for a really long time with this RFC 7432. It was first introduced to be a BGP control plane with new address families to advertise MAC IP information as well as IP prefixes. In the beginning, it was used for MPLS as a forwarding plane. So always keep that in mind going forward, that EVPN is our control plane. And what is EVPN providing for us? Well, control plane information regarding L2, L3 data. It also allows us to provide layer 2 and layer 3 VPN services with a single multi-protocol BGP control plane. So that's pretty cool. And we'll talk about those different services because it also includes things like multicast and multi-homing, which we'll talk briefly about. We'll get into both of those things deeper later on in the week. So if EVPN is our control plane, then what forwarding plane options do we have? Well, MPLS was the original, and that's why EVPN was first created. But for our uses, we're more interested in RFC 8365, which I'm sure you will all read after class. Every word, super interesting. But that's going to be our focus with VXLAN. And VXLAN, of course, extending our layer 2. What types of control plane have we had with VXLAN so far? What did you have to lab up? What did you use to lab up? Or remember from your VXLAN classes?
Sorry, could you repeat the question?
Oh, thank you, Daraj, for helping me out. All right, go ahead.
Sorry, could you just repeat the question?
No. What control plane options do you have with VXLAN?
Oh, with VXLAN.
So we use the flood list.
IP flood list.
Yep, so we can manually build a flood list. And what do we call that?
VTF flood.
What's then a term for that?
Hidden replication.
Exactly, thank you.
Yeah.
Hidden replication, so HER. But obviously there's pros and cons to that. We can also use multicast. We can also use CVX. And we'll go through some pros and cons of that, but
Did Arista not use, didn't we not use, I know some other vendors do multicast. I thought we weren't doing it. We were pretty much going along with head-end replication.
So I only know some older companies in India that have used multicast in the past, but not many customers use it at all.
I mean, that's not the Arista, our official position, right? Is that we don't really support multicast with it.
I would say
we really go with HER.
Our two favorites are EVPN and the
And
HER.
HER, right?
Mhm.
But because I know and I have seen other implementations where, they were using multicast.
Yeah, no, multicast, you have to be running PIM and underlay, and a lot of customers don't like the complexity of multicast. But for customers who use multicast and are going to take advantage of EVPN multicast, then it might not be such a big deal. But VXLAN, yes, traditionally, if you are at smaller scale, then HER works just fine. If you need larger scale, then you're going to use EVPN in the control plane. And that's what this class focuses on, VXLAN as our data plane forwarder. There is a third forwarding plane option, which is just the provider backbone bridging, if you are interested in reading more about that. So if we're taking a look at the model, we have a BGP control plane, and we'll be taking advantage of the multi-protocol BGP and its ability to have address families to encapsulate our VXLAN, or rather for our VXLAN encapsulation. Also, we have a multi-tenancy for virtual awareness through route target and route distinguisher concepts. And then, of course, being able to advertise MAC and IP information through our BGP update messages. In our data plane, VXLAN, just as you all just finished in your class, where we have L2 and L3 encapsulation. This encapsulation is carried out across our VTEPs, which extends our layer 2 between data centers or within a data center. We'll go through a couple of design concepts here. And then we're going to be using the traditional leaf spine topology that you are very familiar with. In the earlier days, we did have the, what was it, the access layer, distribution layer, and core layer. But technology has gotten to the point now where our top of rack switches have a lot more capability as far as L2 and L3 tables. So we have a more condensed architecture, which is leaf spine. We'll talk about some of the different protocols, pros and cons of using those protocols in our layer 3 topology. For the nomenclature, I'll point out the important ones. You already are very familiar with VNIs, or virtual network identifiers. I wouldn't worry about the network virtualization overlay or the network virtualization endpoint. We all pretty much call it AVTEP. We will look at some EVPN instances. So when we set up EVPN, and if you take a look at show BGP EVPN instance, then you'll see what we're talking about here. And that is a fun little command to run to make sure that EVPN is working properly. We will also talk about MACVers. MACVers are just virtual layer 2 bridging domains. So very similar to IPVers, which we will also be using, just layer 2. So we already did cover VXLAN and how we needed to exchange control plane information, how we were doing MAC learning, how we handled bund traffic. All right, let's talk about some of the benefits. EVPN is awesome because you can have a multi-vendor environment. So you can have a pair of Aristas in MI, you can have a couple of Junipers, you can have a couple of Ciscos, and we're all going to be able to talk to each other. We're all going to be exchanging the same route types, and this helps customers avoid this vendor lock-in, which is a really fantastic opportunity for us to get into a customer network that might be purely one vendor. And EVPN is going to allow us to come in. They're going to see how awesome Arista is, and then they're going to boot everyone else out. But in general, it's always good to have something that is open source, multi-vendor, versus something that locks you in. It's why in the beginning, CVX was not a super popular option for us, because it did lock you into Arista. We use CVX in other applications, and I think India really liked CVX. I think they're a little bit nervous about the configuration complexity of EVPN, but then CVP made configuration super simple. Once you had it configured once, you could just push it out as many times as you wanted to. And I think most of our Indian customers are now running EVPN versus CVX. Also with EVPN, the discovery for remote VTEPs is done automatically through route type 3s, which we'll talk about, which is kind of cool. We don't have to manually configure anything. And lastly, MAC address learning through BGP and BGP updates gives us some additional benefits, namely ARP suppression, which we'll talk about later. We still locally learn MAC addresses, but then once we learn that MAC, it triggers something called a type 2 route, which is then shared across all of our EVPN peers. So once you get past all the configuration, then you'll see that the benefits of EVPN, I think, outweigh the complexity of configuration. Additional benefits include allowing route targets and route distinguishers for multi-tenancy. We mentioned ARP suppression, which reduces ARP across your EVPN fabric. We also support active-active and active standby multi-homing. This is important because some applications don't do active-active. So we still have a lot of customers out there who have to have active standby. And of course, with MLAG, active standby is not a possibility, but with multi-homing it is. We also can carry various services across a single EVPN session, which is pretty cool. All right, so let's take a quick look at just a layer 2 VPN service provider example and where we start to see these advantages coming to light. We have customer ABC who has a location off of PE1. And we also have a customer XYZ off of PE1. Both customers have remote data centers where they want to be able to extend layer 2 connectivity. And this could be a variety of reasons, which you're very familiar with going through the VXLAN class. They might be using vMotion. It helps with resource sharing and maximization. It also allows us to reuse information, reuse IPs instead of having to recreate everything when we stand up a new data center. So within the core, we don't know anything about our customer or network structure. This is showing an MPLS core, so we just care about labels. And we're gonna pop and push our encapsulated L2 data between our data centers with no issues. Layer 3, the same thing. And if you think about, all right, these are just some of the design use cases that we have for it. Layer 3 VPN, we're not going to get too deep into today, but that is something that if you've heard the term IRB or integrated routing and bridging, It's just introducing routing into the network instead of just a pure L2. Nothing new from VXLAN. And if we're mixing it up with address families and multi-protocol BGP, you'll see that we can run any numerous type of technology across it. But EVPN with its layer 2 and layer 3 services is significantly better over all of these more traditional technologies that we use across the service provider to provide more or less the same functionality. If we were within one data center, we can do the same thing. We can have multiple services that stretch between different leaf pairs, different top of rack switches. We still want to be able to communicate east-west. And because we're going across a layer 3, we want to be able to encapsulate that without any interruption of service or any fancy configuration. The same with layer 3. So this isn't anything new. These designs aren't anything new from what we learned in VXLAN. The difference now being that we're using EVPN as our control plane. All right, so let's start talking about some of the more interesting aspects of EVPN and how it works and how it exchanges all of the control plane state between our VTEPs. We have this network layer reachability, this NLRI, which is carried in our BGP messages, specifically multi-protocol BGP, because we cannot use EVPN with our gate D BGP. So the original BGP that comes default on our boxes, and I don't know if anyone on the call has information, as far as I know, we will continue to run gate D BGP as our de facto BGP flavor on our boxes, just because it's backwards compatible. If we start sending out EOS running multi-protocol BGP as a default, I think a lot of customers were barking saying that they would have issues. So as far as I know, we still have to make this configuration change on the CLI that it won't be the default. If you do happen to see something, please let me know moving forward. So once we configure multi-protocol BGP, you'll notice some new fields. We've got this AFI, our address family identifier. For our L2VPN, it's 25. Our SAFI is 70 for EVPN. And we're going to see two main BGP updates. And this is going to be multi-protocol reach NLRI and an unreach NLRI. And if you think about that, it's pretty easy. Once we have learned new information, whether an MAC IP or an IP prefix, we're going to send out a BGP update message with some reachability information. And if a host were to leave or a network were to become unavailable, you might imagine we're going to send an unreach NLRI update out. So really got these two update messages that go up. EVPN uses multi-protocol BGP to advertise MAC addresses, MAC plus IP information, aka ARP, IP prefixes, as well as the VTEPs and the VNIs that they are participating in. So keep this in mind when we start talking about route types and which route type sends out which of these pieces of information. All switches participating in the overlays are expected to run EVPN sessions. It's going to be hard to talk to a switch and communicate control plane state with any attached host if they're not. And this is the line of config we need to turn on our AR BGP. It does require a reload of the switch. You can run show IP route summary if you guys happen to have a det up in the background running this already. And when you look at show IP route summary, it will tell you which BGP flavor you're currently running. So at times in the early days, I don't think we get this too frequently now, and I'm sure Showtech Analyzer will point this out in a heartbeat. If they happen to be running this, but they haven't reloaded the switch, they would have issues. Mainly when you go try to configure your address families, it's going to bark at you and tell you that you can't do it. So these are a couple of fields that you'll see when you look at these BGP messages. We'll have our address family identifier, our subsequent address family identifier, which if anyone on the call has ever had an issue with those two fields, let me know. I never have. I've never had to worry about them. The length of the next hop, never had to worry about that. The network address of our next hop. Some reserved information. And then what's really important is the network layer reachability information. So when we take packet captures, this is where we're going to look. And then with the unreach, we're going to have the withdrawn routes. And these withdrawn routes will be withdrawing type 2 routes, type 3 routes, type 5 routes, which we'll get to soon. Taking a look at an actual packet. And if we dig into our BGP, again, we are taking advantage of the flexibility of BGP as a protocol. Here's an update message. And when you drill into the path attributes, we can see that this is an unreachable NLRI. Don't actually see what we are withdrawing here, but you would actually see what you are withdrawing. More interesting, let's look at a reach NLRI packet. And when you drill down into it, we can see that it is a MAC advertisement route, also known as a type 2. You become very familiar with type 2 routes. We have a route distinguisher, which we'll talk about. But hopefully you're all thinking and remembering back to your BGP class, and you already know what the route distinguisher is. The name is a little bit self-explanatory. We'll talk about the ESI, aka the Ethernet segment identifier, when we talk about multi-homing. We'll talk about the Ethernet tag ID when we talk about VLAN aware bundles, which is a flavor of MAC birth, our MAC length, our MAC address. And then here we can see that we have an IP address bound to this type 2. So there are two different types of type 2 routes. We have a type 2 that is pure layer 2. We have a type 2 that is MAC plus IP. As you guys go through your labs, I want you to pay attention as to when you see which type. If we continue down, we have a path attribute called an extended community. This is very important. Why? Look what is in our extended community. We have this construct within BGP called a route target. And a route target is what signals to our VTEPs what control plane state we care about and which control plane state we don't care about. We can also look and see what we're actually encapsulating here. Our forwarding plane is using VXLAN versus MPLS or something else. So if you look at our two important path attributes, our multi-protocol reach NLRIs or unreach, and then our extended communities. So how is MAC learning done in EVPN? We know in VXLAN, if we're just flooding information, then we are going to flood BOM information based on our flood list. And we still have ARP requests going back and forth across our VXLAN fabric, unless we're using direct VXLAN. Well, no, then we still have ARP requests going back and forth. But here it's a combination. Here we're going to use both data plane learning and protocol learning through EVPN. The data plane learning is nothing new. If we have a local host attached, then as soon as he first starts communicating with his VTEP, then the VTEP is going to do totally normal layer 2 MAC learning and populate his MAC address table. The difference is now when this VTEP learns the source MAC on a local interface, then it is going to advertise this MAC address via a type 2, which we are looking at here, via this type 2 advertisement route out to all VTEPs in his flood list. So if you did a show VXLAN VTEP flood or show VXLAN flood VTEP, whatever the command is that I always forget, then you will have a list of your VLANs and your VNIs, just as you do in normal HER VXLAN. But the difference is how we're building that flood list. We're building that flood list using a special route type called a type 3 IMET, which we'll talk about. But because those type 3s have built our flood list, once we learn this new MAC address and we create a type 2 route, we send those advertisements out to all of those VTEPs that we've learned through EVPN. So it's a dynamic learning versus a dynamic sharing of MAC and MAC IP state through our dynamic building of our flood list. All right, when we are talking about pure layer 2 communication, then we have a construct called our layer 2 VNI. And we know what a VNI is, just from VXLAN. There's nothing new with that. And you might recall, and I would ask you guys questions, but you seem to be quiet. So actually, no, let's ask questions. You guys know I like asking questions. How do we configure our L2 VNI in VXLAN?
We just map it. You
We
want
do mapping.
Yep. No, you guys are absolutely right. Don't be shy. We just map our VLAN to VNI, right?
Mm-hmm. Yeah.
So nothing's changed here. What we are going to do is we're going to have our layer 2 VNI, however we could configure it. We could configure a range, or we could configure it individually. These are going to be mapped to this new concept of a MAC birth. Again, a layer 2 construct where this is providing us information on our data plane forwarding. This is giving us control plane state on our layer 2. So data plane, control plane. And this L2 VNI will be in all of the type 2 routes that we send out, as well as our type 3 routes. This is sharing host information, and this is building our flood lists. And remember, our flood lists are responsible for all of our BUN traffic. If we add layer 3 here, so if we start configuring SVIs, Then we're gonna have the second type, which provides us our ARP control plane state. This VNI is the same VNI that's going to be present in our VXLAN header, where we're going to be doing our mapping and our reverse mapping at the remote VTEP. And when the remote VTEP receives this type 2 or type 3 route, then the VNI is going to tell us which MAC address table, aka MACVerf, it should either perform the lookup in or add information to, and then forward it according to our inner Ethernet header. The layer 3 VNI corresponds to the IP VerF. So I always like throwing a little IP in just to keep things straight. Traditionally, we've only had one VerF, which stood for virtual routing and forwarding, that service providers use to provide multi-tenancy to their customers. VerFs have been around forever. We modified it to use it within the data center and we called it VerFLite. We're using it again for EVPN and we're calling it an IP VerF. So we have a MAC VerF for our layer 2. We have an IP VerF for our layer 3. We have an L2 VNI for our data plane forwarding. And now we have this L3 VNI for our layer 3 forwarding. The layer 3 VNI will also be mapped, but instead of mapping a VLAN to a VNI, now we're going to be mapping a VRF to a VNI. This is our data plane, and the IP VerF will be our control plane. So once we are using IRB, then we'll have this layer 3 VNI. I do want to point out it's specific to symmetric IRB. The two main flavors are going to be asymmetric and symmetric. And we'll talk more about that when we really get deeper into layer 3. This is more just an introduction. The L3 VNI is also going to be encoded in our type 5 routes. Type 5, which we're just now, this is the first time we've mentioned it, includes our IP prefix information. So if we have a connected route in our RIB, once that's configured, then we will send out a type 5 route advertising our /24 or our /23 or whatever our prefix is. This layer 3 VNI will be included in the VXLAN header. And it's going to signal which routing table, aka VerF, it should perform the lookup and forwarding operation in when looking at the inner IP. So layer 2 VNI, layer 3 VNI, MAC VerF, IP VerF. Any questions on the L2 and L3 VNI constructs? We'll definitely be getting back to them. So let's take a look at the first 5 route types. I think we're up to a lot of route types with EVPN. There's a ton of flexibility with EVPN. I'm sure that number is only going to grow. But the main ones where we care about, especially for the beginning of the class, is going to be the type 2 MAC address route. Remember that there are 2 types of these, one with the MAC and one with MAC plus IP. The type 3, which is the inclusive multicast Ethernet route or our IMET route, which builds out our flood list for bump traffic. And then the type 5, use purely in symmetric IRB to advertise prefix routes. Type 1 and type 4 are used in multi-homing. Type 1 is going to discover all of your segments. So one of the advantages of having multi-homing is you aren't limited to 2 devices like we are with MLAG. You could conceivably also have an Arista device, a Juniper device, and an Extreme. Why you would ever want to do that, clearly nobody ever would, but you could have numerous devices here, all advertising their ESI and finding each other. Oh, actually, that's type 4. Type 4 is what allows peer discovery on your ESI, and then we'll elect the designated forwarder. But we'll talk about those later on.
Do you support type 1 and type 4 in Arista?
So type 1 and type 4 are used for multi-homing. So type 1 is for forwarding and remote discovery. I'm going to have to add some verbiage to this because I think it's a little bit confusing. Type 4 definitely is it. Type 4 routes are going to be sent out to discover who else is on your ESI. In MLAG, it's really easy because we're connected to each other. In multi-homing, we're not connected to each other. We're connected through each other through layer 3 connectivity through a provider edge device. So we'll send out these type 4 routes to find each other.
Does Arista devices support type 1 and type 4 route types?
We do, absolutely.
Okay, because in some vendors, I think they do not support all types. Just asking.
Good to know, but yeah, no, we absolutely do.
Oh, cool.
All right, so we've talked about the type 2 routes being our MAC control plane state information. Type 5 is carrying our IP prefix information. Type 3, let's talk a little bit more about these IMET. And once you have configured your MAC-VRF, which again is your layer 2 control plane information under router BGP, then it's going to send out a type 3 route advertising VNI to VTEP mappings. And basically what it's advertising is telling other VTEPs, I'm interested in bump traffic for this VNI. So if my VLAN 10 is mapped to VNI 10, and I have a MAC-VRF for VLAN 10, once everything is configured correctly, I will immediately start sending out type 3 routes to all of my EVPN peers. Eventually my remote VTEPs, if I've got some transit spines in the middle, eventually my remote VTEPs will receive this type 3 route from me. And if they have that MAC-VRF also stood up with the correct route target, then they will add me to their flood list and say, hey, I get bump traffic for VNI 10 because I've got VLAN 10 locally attached hosts. So if I do receive bump traffic or need bump traffic, then I will send it out to me. So type 3 is just building out our flood list. All right, and then type 1 and 4, we talked about. Type 1 announces reachability of multi-homed Ethernet segments. So type 1, there's a couple of multiple uses for type 1. But one of them is just out to all remote VTEPs, letting them know they exist, whereas type 4 is more local, just looking to see who my local segment is, who's part of my local segment. All right, what have we not covered between the MAC-VRF, which is our layer 2 bridging table, and our IP-VRF, which is our layer 3 table? So MAC-VRFs can contain one or more bridge tables. It's not a one-to-one. We'll talk about that. One is called a VLAN aware, and one is called a VLAN aware bundle. Or sorry, we might just call it a VLAN MAC versus a VLAN aware bundle. MAC version. I think we get into that. All right, we'll get into the two different types of MAC that we support. There's actually 3 of them, but Arista only supports 2 of them in a couple slides. But first, let's go through route distinguishers, because these do play a big role in EVPN. Really, the same role that they've been playing in BGP in the service provider world. A route distinguisher is simply a deterministic ID that gets prepended to a route entry to make this route globally unique. And it's, let's go through if it goes through all the pros and cons. This allows for overlapping addresses to be installed in the global route table, but still be unique. Because otherwise, what would happen if I say I am a PE router and I get 2 identical routes from 2 different customer edge devices, but they're the same route? What will happen? Will I install both of them?
No, one of them will be deprecated.
Right, so it's just going to be the latest route I get, I'm going to assume is the best one to use, and I'm only going to install one. The same thing is happening here. If you are running multi-tenancy and you are duplicating VLANs, or if you are using multi-homing or MLAG, and you still want to have unique identifiers just for redundancy in case of failure, then you're going to use a unique route distinguisher. So when we assign a route distinguisher to our MAC verb or to our IP verb, then this will tag any routes in those verbs with our assigned route distinguisher. And this could take a couple different formats. So it could be your loopback 0, which is unique. If we are in MLAG, our loopback 1 is typically used to be our VXLAN source interface. And since we want to be one logical VTEP, that will be identical across both. But for redundancy, we will use loopback 0, which is our BGP router ID, typically used in EVPN as the source interface in EVPN. So we could use that same IP. We could use MAC, we could use IPv6. Traditionally, what we see is the loopback 0, and then the VLAN or the VNI. Typically, this is what we see the most: the EVPN IP address and the VNI. The important thing is that it is deterministic. So if you're building out your own network and you see a particular route, you want to know right away who originated that route. So when you build your own network for the lab tonight, then keep that in mind. And then there's route targets. Same thing as in BGP, it's going to control which routes we import and which routes we export into and out of our L2 and L3 verse. When control plane state gets exported, they're assigned a route target ID. And who remembers when we looked at that packet capture, which path attribute contained this information? Does anyone happen to remember that?
Extended community.
Yep, thank you, Anton. The extended community is a path attribute that if it does not get carried with our BGP update, then the route target won't be included. And as you might expect, when this BGP the message gets to the remote VTEPs, they'll just drop the information. They won't be able to import it because they won't know to import it. Oh, oops, it's right here. I should actually read the entire slide before I start talking about it. But good job, Anton, you're way ahead of me. All right, so yes, the route target is in that extended communities attribute, which you may or may not remember from the previous slide. And the route target will typically take the format of the VNI colon VNI or VLAN colon VLAN. It can be whatever you want it to be. You can also auto configure the route target, but we don't typically recommend auto configuring anything. In multi-homing, we might auto configure the LAC PID, but you'll see why when we get to multi-homing. All right, so let's look at a quick example where we have switch 1 on the left. And it's sending out a couple of type 2 messages where we have the route target 100, 100 and a route target of 200, 200. And on switch 2, we've got 2 layer 2 MAC perfs. And thankfully, because things are configured correctly, we will receive this message and we will import the data it contains into our layer 2 bridge tables, as you can see here. However, oops, we don't have the however. Oh, maybe it's the, but if the route target is incorrect, or if we wanted to do route leaking, then we can play with route targets to make that happen. All right, so let's dig into extended communities. Extended communities are included in all advertisements, if it's configured correctly, to determine our data plane encapsulation, as well as signaling other actions we applied, such as our route target. And you can see some of the information that can be included with our extended community values. We can skip over this. The big thing here is to make sure that we are sending the extended community in our BGP message. So we've already talked about broadcast and unknown unicast. We'll send that information based on our flood list. If we want to talk about multicast traffic, then like it states here on the slide, there are a lot of caveats. The big thing here is that we don't support IGMP snooping. I believe this was also true with VXLAN. So what we have is new route types for multicast. We won't get into this, but just be aware that route types 6 through 11 provide us control plane state for IGMP snooping, and for PIN. So time. Oh, go ahead.
So these would be used like, not if we're using, multicast, for learning, this would be used to just support multicast as a service.
Correct. And when we get into EVPN multicast, you'll see that one of the solutions is running PIM in the underlay. And if a customer was using multicast and just sending out a group for bum traffic, I mean, that's all it is. We're concerned with bum traffic. And if we say use this SG group for all bum traffic and just have all VTEPs be receivers to that group, That's how multicast works as control plane for VXLAN. Then doing something like this, if you're running a bunch of multicasts, is not that big of a leap because you're already running PIN in the underlay. The caveats that we'll get into, we didn't support it on, we didn't support multicast with BART for a long time, but we do. Now we had some issues with Anycast Gateway, but we have solutions to all of the initial problems or limitations earlier in the day. But once you understand type 2, 3, and 5, the rest of this, it's just new route types. But each of these route types are providing us some sort of control plane state. It's just, what is a control plane state? Do we care about IGMP joins and leaves? Do we care about PIM? So don't worry about EVPN multicast. Once you get EVPN and the basic route types, then the rest of this is pretty smooth sailing. I feel like we've gone through this a few times, but we'll go through it again. Our type 2 routes advertise our host MAC addresses. So every time a VTEP learns a new MAC, it's going to send out a type 2 update. This update is going to be sent to every VTEP in that VNI. There's an optional IP field if we're dealing with layer 3. And our MAC plus IP is identical to receiving an ARP. And this will populate our ARP table. When a VTEP receives a Route 2 update, it's also importing the remote VTEP and VNI information along with the host information. And this gives the MAC for the control plane state related to how to reach a remote MAC. So L2, we can get to this MAC 01 via this VTEP using this L2 VNI.
So does VTEP like immediately advertise these routes when it's, let's say, learns like new MAC address? Does it happen like instantly, or there's some like timers?
Happens instantly.
Okay, so like if you have like thousands of MAC addresses, so there are like literally thousands of updates going on like every second, right? Like in large domains.
We will talk about this, but to answer your question, because I know that you were just full of suspense, and so is Mihir. I know Mihir and Duraj are sitting there thinking, oh, I can't wait to hear this answer. That as soon as that BGP update gets sent, that state will remain on all remote VTEPs until there is a withdrawal message sent in the form of that unreach NLRI. So as long as that host is talking, then we'll maintain state.
Okay.
But if you do have thousands of hosts coming and going, then it will be generating a lot of type 2 routes. And perhaps depending on timing, there might be a large BGP update message that gets sent.
Yeah, we can have like thousands of VNIs, and each VNI have like thousands of MAC addresses, right? Like in typical data center network. So
that's more of an, I know that we have a route type, I'm pretty sure it's route type 1 will handle this in multi-humming, but it's in just normal everyday, I haven't seen any issues. I don't know if anyone on the call has taken a case on this.
I'm not sure, but maybe
There's a mass withdrawal, I know, with multi-humming. Go ahead, Anton.
maybe we do not generate
like sort of dampening.
single BGP update for each.
We do have MAC
okay.
dampening, which we'll talk about, but I don't, Guy, is that
I
what
mean-
is that what you're referring to?
And then we can place, for example, 100 MAC advertisements in the same BGP update, maybe.
Yeah, we can combine like, but let's say like we have only one change in our like VTEP, right? Yeah, we can definitely combine all these like different types or even different like
Yeah.
types of address families, right? With single update, but here just wondering, because BGP is known for its stable state, right? Like internet routing protocol of internet. So
I mean, in
Well,
EVPN,
having a host update message sent out won't destabilize BGP. The short and simple answer for this is that it is an immediate triggering of a type 2.
okay,
But if the host is stable,
okay.
then the
And
BGP won't be stable.
This combination of IP and MAC in a type 2 is like as a like ARC, right? For mainly for ARC, right? For ARC table. Okay.
So when we're talking about layer 3 routing, specifically with symmetric IRB, then we'll actually need this. But if we're talking about L2VPN or asymmetric IRB, then we're going to actually be bridging across the EVPN fabric and just using the L2VNI. So that's why I wanted you guys to pay attention, because I know this causes confusion on the floor. When do we expect to see the MAC, and when do we expect to see the MAC plus IP? But both of them are type 2. All right, if we're looking through the fields that get sent out in our BGP update, we'll have the route distinguisher. Note that the route distinguisher is not located in the same attribute as our route target. So the route distinguisher will be sent out with our NLRI, as well as additional information depending on what flavor we're running with our MAC, the optional IP, and our VNI. So remember, we have to signal our MAC berth. The route target is in our extended community, where we also have a couple of other fields, such as I guess we'll talk about MAC mobility in just a second. What else do we have here? So the extended community carries the system MAC used with symmetric IRB, not used with asymmetric IRB. We'll get into this then. All right, so one of the huge advantages of using EVPN is ARP suppression. It's also known as ARP proxy, and it's sort of a chicken and egg, because our VTEPs are learning about remote. Okay, I'll just walk through the slide instead of just talking off my head. So your local VTEP, if I'm Corey and I'm attached to VTEP 1, and I've been talking to my VTEP, so my local VTEP knows about me, and now every other VTEP knows about Corey, because this local VTEP has sent out a type 2. Then what happens if Rich is over on a remote VTEP over here, and he wants to talk to Corey, but he's never talked to Corey before, he's going to send out an ARP saying, hey, where's Corey? Well, Rich's local VTEP will say, I know where Corey is. He's way over here, but I already have his information because I received a type 2 route and I've populated my table. So this remote VTEP will snoop on Rich's ARP and reply to it. So this is that ARP proxy that is going on just inherent in EVPN. And because of this, we have ARP suppression, because Rich's ARP doesn't need to go across our EVPN fabric over to all of the VTEPs that are in our EVPN domain, where Corey can then respond, or the local VTEP can respond. So ARP suppression is a natural result to the ARP snooping or the ARP proxy that we're doing, because we already have the information. As soon as Corey is learned and that type 2 gets sent out, then every VTEP knows about Corey. So this slide is all about just something that EVPN does by nature. Any questions on ARP suppression, aka proxy ARP, aka ARP snooping?
No.
Yeah, no, I mean, EVPN, it's a lot, but as soon as you start digging into it, it's pretty intuitive. It makes a lot of sense. So once you wrap your brain around the configuration for it and think about all the constructs that you need, which we'll go over a lot. So by the end of this class, you guys will be EVPN experts. All right, so let's talk about MAC mobility. And if we've got a lot of vMotion going on in a network, how are we going to handle that with EVPN? And the answer is that our route updates have sequence numbers that are in our extended communities. So yet another piece of information that if we're not sending extended communities will cause a problem. And these sequence numbers will be updated when there's a move. So for example, if a VM moves to a new host, the new switch will learn that MAC address of the migrated VM locally. It updates its MAC database and increments the sequence number for this MAC by 1. The new switch immediately sends out a type 2 update for its new MAC with the new incremented sequence number. All remote VTEPs, including the original VTEP, will see the updated sequence number, flush out the old MAC, and populate the new MAC. Simple. I don't think I've seen any cases on this. So in addition to MAC moves, we also have a protection mechanism which detects and prevents MAC route flapping between VTEPs. So if we have duplicate MACs, if we have any sort of instability in our network, then we can see a whole lot of MAC flapping. If we detect this MAC flapping, then we will activate dampening. We generate a syslog message and we'll stop sending and processing updates for that MAC. Now what this is, I'm pretty sure, even though it doesn't say this on the page, I think this is when you get the blacklisting of MACs. And you actually have to go in, you might get a case, and we certainly did in the early days, where all of a sudden hosts would lose connectivity. And it might have been after a network event or after some configuration changes. And all of a sudden I can't reach this host. And you look and look and look and it looks like it should work. But then it ends up that that MAC was blacklisted. ShowTech Analyzer 100% checks for this. You can look at the blacklisted MACs yourself and see if there's anything on there. and then you have to remove it manually. If there's a customer that is using vMotion a bunch, I think it's 10 moves in a certain amount of time, which we can probably tweak that. But you can create an event handler where if you do experience this MAC blacklist frequently and you know it and you expect it, you can create an event handler to just boot the MACs off the list whenever it occurs. So apparently it's 5 MAC moves in some sort of second. 180 seconds. That seems high to me. But in any case, we do have this if we have a whole lot of MAC flapping going on. Any questions on MAC moves or MAC dampening? So let's review our type 3. Again, our IMET routes, inclusive multicast Ethernet tag. I will tell you, I always forget what it actually stands for. This is the control plane information that is going to build out our flood list. So anything, any VTEP that is interested in a particular VNI, the type 3 routes will go out, and all remote VTEPs participating in that VNI will add you to their list. And then if we receive ARP, if we receive unknown unicast, and we will just flood out multicast. We don't have IGMP snooping turned on. It will cause problems if it is turned on. And we'll send it to everything that has been dynamically built in our flood list through these type 3 routes. So if you want to catch a type 3, make sure that you're running your TCP dump before you finish configuring everything to catch it. And just to this last bit, that if we do get an unknown unicast packet, for example, then we will use ingress replication. And what we'll do is we will make the number of copies needed to go to each one of the remote VTEPs in our flood list. What is in a type 3 route? We've got our route distinguisher. We have our VTEP IP. We have our extended community route target, very important. And we have our VXLAN antenna encapsulation community. At this point, we don't need to worry about the PMSI. But we will talk about that when we talk about other EVPN services at the end of the week or early next week. All right, last but not least of the route types we want to focus on today is our type 5 route. And this is just sending prefixes. So type 2 routes are either sending MACs or they're sending what we call host routes. So a /32 or /128 if they're running IPv6. So this is a host route, not a prefix. Type 5 routes are not bound to any particular host. They are just advertising routes and subnets.
So this is like a standard layer 3 VPN, right?
Yep.
Just advertising purposes. Okay. So just in order not to run like additional address family, we just like have new type.
Yeah, we don't need any additional, this is all falling under the EVPN address family. All right, so let's talk about the different flavors of the MAC bursts that we can have, those layer 2 bridge domains that we're building under EVPN under our router BGP. We only support 2 of these. We support VLAN based and VLAN aware. So if a customer is running 2,000 VLANs and they don't want to have to manually define each one of those VLANs using a 1-for-1 VLAN based MAC-burst, they can use a VLAN aware. You don't want to have VLAN based on some VTEPs. For example, say I have 3 VLANs, 10, 11, and 12, and I've manually configured it on 4 of my VTEPs. Well, then I add 2 new VTEPs and I decide, well, I'm just going to use a VLAN aware bundle and just put 10 through 12 or whatever my range was on a single MAC-burst. That won't work. So my VLANs need to be consistent. I can't have VLAN 10 be in a 1-for-1 VLAN based MAC-burst across all my VTEPs. And then I can have VLAN 11 through VLAN 3000 as a VLAN aware bundle MAC-burst. So let's take a look at what that looks like. This is a VLAN based. So you'll notice in the diagram, it's a 1-for-1 where I've configured a MAC-burst for VLAN 200 and a MAC-burst for VLAN 100. And then I would have that across all my VTEPs. So these are dedicated 1-for-1. You'll notice that there is no tag that is included in any of our fields within this packet. We don't need to. It's 1-for-1, so we don't need to. Also note, which I think you guys covered in VXLAN, that there's no VLAN tag that gets carried across. It's the VNI that gets carried across. If we were to look at a configuration example, it's really straightforward and it's what we've already covered. Remember, BGP, or specifically multi-protocol BGP, is the magic under all of this. And using these 2 constructs, we've got 2 MAC-bursts here, VLAN 100 and VLAN 200. Each one has a unique route distinguisher, which means that any of our MACs learned locally will be sent out using this RD. My route target for both importing and exporting control plane state is 100, 100. And then I'm going to redistribute learned. Any MAC I'm learning locally, I'm going to redistribute into EVPN. And the same with VLAN 200. My RD is going to be my VTEP and VLAN 200. Or this could be my VNI that I'm mapping my VLAN to. So really simple, really straightforward, but if I have a whole bunch of VLANs, I'm not going to want to use this. I'm going to skip the bundle service because we don't support it and I haven't heard anything that we are going to support it. But feel free, you all have access to these slides to take a look. I'm going to try not to fill your brains with what you don't need to know right now. So VLAN aware bundle, this is used frequently with our customers. And the difference being, instead of 1-to-1, now we're N-to-1. And the way we do this is using this Ethernet tag, which you might remember seeing in when we've looked at the fields. And this Ethernet tag can either be, will be set to the VNI, not to the VLAN. So you'll notice here that when we look for the EVPN instance, which is just the MAC-burst or the IP-burst, then now we have multiple bridge tables within this one instance. And we're going to be tagging this traffic to keep it separate with this Ethernet tag ID. So what does that look like here? Instead of having that one-for-one mapping, now we're going to use VLAN aware bundle, and we're going to give it a name. So here we're going to put all of these VLANs 10 through 99 in this tenant A VLANs, and we could have a second VLAN aware bundle called tenant B VLANs with VLAN 100 through 199, for example. As for all map first, I'm going to need a route distinguisher that I'm going to append these type 2 routes. I'm going to have a route target, which will be tagged for both imported and exported, or tagged on the exported routes. And if imported routes come in with this route target, then I will process them. We will redistribute any learned MAC information, any host information. We do need to specify which VLANs are part of my bundle. We're also going to give them the Ethernet tag ID. This tag ID will be carried across our EVPN fabric. And you want to make sure that we keep them straight here. I don't know that anyone, I'm sure people have typoed everything, so probably someone did typo this, but just keep them in mind that it's this tag that will take them from the control plane and put them into the data plane. So it needs to be correct. Oh, actually, I was totally looking at this as a misconfiguration, which it could be a misconfiguration. But notice that if the customer wants to do some VLAN translation, that you could do that using this Ethernet tag ID. So out of mistakes can come opportunity. And just a quick summary, VLAN base is going to be a 1-for-1, one VLAN for MacBirth. Or if you have multiple tenants, then you can use a VLAN aware bundle. Or if you have a large scale and you don't want to type everything out, then you can also use a VLAN aware bundle. Any questions with VLAN or VLAN aware bundles? So just a brief overview of multi-homing, which is another EVPN service. We can take it, we can use active-active or active standby with multiple, not just 2 devices. So depending on host application, they might need to use multi-homing. But it's very similar to our MLAG idea, where you have at least 2 devices forming one logical customer edge device, which gives us higher capacity for all active links forwarding or for failover. MLAG is proprietary to Arista. Which you're all very familiar with. Or we could use this multi-homing with our route type 1 and 4. some of the differences, which I'll get into when we get into multi-homing. There's no peer link, so there's no additional cost of connecting our devices. There's a difference in load balancing, which happens in the underlay versus the overlay. We can have more than look at this. It says here that right now we max out at 2. But we'll get deeper into multi-homing when we're focused on it. So let's just go ahead and skip this. This is the MLAG. And the difference, if we're multi-homing, we wouldn't have that peer link. We would use Ethernet segment identifiers to create our logical formation. All right, before we start talking about some of the design concepts, let's take let's do a 10-minute break. It's 1:25. Let's be back here at 1:35, and we'll start talking some design. And then, because I really want to go through an example on the CLI. So 10-minute break. I'll see you guys at 1:35. All right. So we know, as far as design goes, that we have 3 different data plane choices. MPLS, I'm sure we'll move into it as we get more service provider customers. But for right now, we're focused on VXLAN. A quick recap of VXLAN. I know it's been a couple weeks for some of us and possibly longer for others. VXLAN is simply a layer 2 tunneling protocol that runs over any sort of L3 IP network. Sometimes we call it MAC in IP encapsulation. The header size is 50 bytes, 14 bytes of L2, 20 bytes of L3, 8 bytes for our UDP, and 8 bytes for our VXLAN header. If there's an Ethernet tag, it will go up to 54. I've still to this day not seen someone actually include this VLAN information, but perhaps we will one day. We do recommend configuring the max MTU on all interfaces facing the fabric, due to the fact that VXLAN doesn't support fragmentation and uses the do not fragment bit on all packets to the fabric. Hopefully this is just a real easy refresher for you guys. I do want to make sure we review the configuration for VXLAN, because this is all of our data plane information. Nothing new. We will drop into our VXLAN 1 interface mode, set the source interface to be loopback 1 in most cases. Loopback 0 is used as our EVPN source. As always, our UDP source port is 4789. Or sorry, destination port. And then we'll have our L2VNIs mapped here, and our L3VNIs mapped here. So remember when we were talking about the L2VNI and the L3VNI, this is what we were talking about. So these are the 2 data plane constructs that we use on our VXLAN overlay. If we are only running layer 2, we're only concerned about our VLAN to VNI mappings. We won't have any layer 3 VRF to VNI mappings. All right, so we have 2 pieces of our puzzle here. We'll get to the other 2 pieces of the puzzle, but let's right now talk about underlay versus the overlay, because I know you guys hear those terms a lot. The overlay is just one type of network running on top of another type of network. So our underlay here, well, it's, okay, it says for VXLAN or MPLS. Our underlay is going to be our IP infrastructure. Whatever we're running, whether it's static routes or an IGP, our underlay is that layer 3 connectivity. The overlay is our VXLAN. It's also EVPN. So we have a VXLAN overlay and an EVPN overlay. They're both overlaid on top of this layer 3 connectivity, whatever it is. But VXLAN is our forwarding plane, and EVPN is our control plane. So hopefully, if you're just not even looking at this slide, you think the underlay is simply my layer 3 connectivity between all of my VTEPs, and my overlay consists of 2 parts: my VXLAN forwarding plane overlay and my EVPN control plane overlay. So what are our best options as far as design goes for our layer 3 connectivity underlay? Here, if we start with pros and cons of an IGP, such as OSPF or ISIS, it says that there used to be scale limitations, but now we have ways to scale into these big dense topologies, so you don't necessarily immediately rule out one of these IGPs. The peering is dynamic. We talk about having a faster convergence than BGP, though depending on scale, that might be so minimal as to not be a big deal. Plus, with OSPF, we're exchanging the entire database versus just updates. One of the pros of having an OSPF or an ISIS underlay is that it's different than BGP. So it's really obvious to see, this is my OSPF underlay, and this is my EVPN BGP overlay. You'll run into customers and their router BGP configuration is huge. They have a ton of VLANs, they have a ton of VRFs, they have a ton of neighbors, and a lot of knobs have been turned. And if their underlay is also BGP, it's just that much bigger. So it can add complexity when you use BGP altogether. However, if you are limited to OSPF or ISIS and you wanted to or needed to have specific traffic engineering decisions or pathways, then of course you're limited. And you're still not getting away from BGP because you still have to have it for EVPN.
So do you think it's really, just for the, for this, even though you're using a different routing protocol for the underlay, it makes the config a little easier to look at if you're just using, if you don't use BGP for both?
Yes.
And is that what most people do, or are there people that just like to be all BGP?
From my experience, and feel free others on the call to speak up, but from my experience, most people use BGP in the underlay. However, I know in POP, they use OSPF or ISIS just to show a difference, unless of course the customer has specified, I want to use iBGP or eBGP. Cases, I've seen a couple cases where it's ISIS or OSPF, but the majority of them are BGP.
What about, so, and the really, as far as memory and, utilization, it really, either way, it shouldn't really be much of a difference if you were to use a different underlay. I mean, you're going to run another process, but if you run all BGP, you're putting a lot. Is it like a wash?
That can be done, and platforms have gotten to the point where those differences just aren't as noticeable. that people still will make arguments. I just got a notification that my internet VPN is having issues, so please let me know if you can't hear me.
Okay,
That it's negligible, the differences, and it's gonna come into what does your network engineering team feel most comfortable with?
yeah,
And unfortunately, since we're going to EVPN BGP, then you have to know BGP anyway, so that you can't say, well, no one on my team knows BGP. If you're going to use EVPN, you're kind of stuck having to learn it. There are threads if you search on them, whether to use OSPF or ISIS or BGP, and the conclusions are different every time. Everyone's got a personal favorite for why they're going to do one or the other. I would say the debate is ongoing, and it really just depends on customers.
yeah. I mean, I see the big advantage of is if you use either ISIS or OSPF, you can very quickly look at the underlay without having to try to segregate everything out of BGP.
Once you start looking at BGP enough, then it's not that bad.
Okay,
And you can quickly eliminate that as a root cause just by doing a show IP BGP summary. And if that's good, then you can roll out the underlay.
I mean, in BGP, you're just really using for the underlay, you just really have the global routing table, right?
Yes.
Okay. Thank you for that.
Of course, of course. Thank you for speaking up. And it is an ongoing debate, and design will constantly change depending on what the latest issues are and latest features are and how the platforms change. But BGP, it's been around for years. It's well proven. It's scalable. We're doing update based versus updating or sharing the entire database. We have multiple paths, lots of granularity when it comes to writing policies. And I guess it's an advantage for some folks to have a single protocol versus multiple protocols. But yeah, Ken, let me know if you have any customers that feel strongly one way or the other. But we see it all. Here's what's interesting. iBGP. Now, we've had 2 recent cases where customers running iBGP, they're not full mesh, they're using route reflectors, and their configuration is so crazy that the second time I'm helping on this case, and Joe was like, yeah, it's the same case that has a monitor session issue, because this is a bug where you will get a VXLAN routing loop if you have monitor sessions configured on interfaces that are not being used. And I would say it seems like a really rare case where customers would just configure a whole bunch of monitor sessions on interfaces that don't have transceivers in them or are shut down or whatever. But now we've hit this bug twice. Once with this customer and once with another customer months ago. But it's just this funky thing with monitor session. Keep that in your back pocket. But in any case, this one customer who is using this iBGP, I'm not quite sure what it's giving him. So I don't know really the advantage he gets from having everything in a single ASN, especially with all the other wacky configuration that this guy has. Yeah. So I would say that for the most part, you're gonna be using eBGP in the underlay. And I've only seen this one customer using the iBGP between your spines and your leaves. We do use iBGP between our MI peers. But, and this one example that I have of a customer who used iBGP, I'll dig out the case number and I'll send it out to you guys so you can pull up the show text, or better yet, I can just share with you the show text, and you'll see that the configurations they have on these VTEPs are just crazy. Plus, they're not using the spines as true route reflectors. The spines are also acting as VTEPs. But anyhow, I digress. IBGP, it is an option. I don't know if I would use it. EVPN is, I would say, the favorite underlay, or the one that I see the most. Very scalable. We use this route servers. So in our diagram, S1 and S2 are route servers. They don't have any VXLAN configured on them. They are basically taking EVPN routes and sending them to all connected EVPN peers that it has. Very fast convergence. You can actually run IBGP between the leaf pairs. We typically do. There's a corner case why you want to use this, depending on if you have a link to a spine that fails. And then you'll just use different ASNs based on whatever your design choices is. But this is the one that I see most frequently.
Sarah, just a quick question. In the cases where we have spines acting as a VTIP, do we call them service leaf switches?
So it depends on what their functionality is. If they are serving as the service leaves, meaning they have services off of them, like firewalls, load balancers, then I don't know why we would even call them spines. If they are just, if we really don't even have any spines in our topology, everything is serving as a VTIP with different functionality, and we're just running layer 3 point-to-point connectivity using IBGP or whatever underlay, then they would just, when you hear something called a border leaf or a service leaf, it just is telling you, giving you more information as to the functionality on those VTIPs. Border leaves are going to be connecting data centers. So you'll have your DCI connects there. Your DCI, your data center and interconnect there.
Okay. Thank you.
Of course, good question. All right, so that was for our underlay. And as long as it's good and successful, it can be just about anything. With pros and cons, but all dependent on the customer and the customer's needs. For the overlay, we can use IBGP or EBGP. If it's IBGP, then we're going to have to use rubber reflectors or full mesh, because that's just the rules of IBGP. And then with EBGP, we're going to have the spines acting as route servers. We're going to use our loopback zeros for our EVPN pairings with both scenarios. And then if we're using EBGP in the underlay, I disagree with this. We're not defining a new ASN. We do define a new neighbor. In our underlay, we're going to use our locally connected interfaces as our BGP neighbors. In the overlay, we'll have a different peer group. So maybe that's what it's trying to say, because you can have a peer group for your underlay neighbors, because they'll have a set of characteristics or attributes. And then you're going to have a new peer group in the overlay that's going to have a slightly different set of attributes. So for example, the peer group in the overlay the local AS is something different as well. All right, let's just skip over this because I disagree with this bullet point. I'm gonna have to revisit this. Because you can only have one ASN. You can only, BGP is an application. It's a not a traditional routing protocol. It's more an application or a process, and you can only run one BGP process at a time, which is going to have its ASN. So anyhow, we'll break up a configuration. We'll break it apart as far as the underlay and overlay. So some advantages to IBGP. We're just using one AS number here for our network. Less resiliency, more configuration per device, inconsistent spine configuration, requires local AS support. Yes. And using eBGP, we can have spine switches either be transit routers or route servers. The route server just re-advertises all the EVPN information to our other VTEPs. The route server doesn't change the next hop, retains all of the communities. Yes, I'm not quite sure what the difference is between a route server and a transit router. I feel like everyone uses those interchangeably. I'm going to need to just double check that. But in my brain, I use this interchangeably and they both do the same thing. We're not going to change the next hop. So route servers with eBGP. Advantages, we have consistent configuration across the spines. We avoid all of that route reflector and local AS configuration. We don't need to use the add path. And disadvantages is going to be the confusing multiple BGP sessions. And then allow AS is required if ASNs are reused on a leaf layer, which they're typically not. Usually the leafs will have different AS numbers. Okay, so let's go through some BGP configurations. We'll start with simply turning on the process and assigning it its ASN. We'll give it a router ID. Typically, this is going to be our loopback 0. We're going to turn off our default IPv4 unicast. And the reason we do this is because our gate D BGP, our original BGP, only used IPv4. We didn't have address families. We only had the IPv4 address family. And just because this is part of our default code, really everyone's default code, we want to turn it off because we're going to use address families instead that you see here at the bottom. If you leave it turned on, then it changes the behavior of the configuration here in this section. So we recommend turning it off. Maximum pass with here 2 and ECMP of 2. This is telling us how many redundant paths can we have. We're going to set this number to however many spines we have. If we have 4, it's going to be a 4. If we have an 8, it's going to be an 8. If we don't configure this, say we leave this at 2 and we actually have 4 spines. That means that the maximum number of paths I will put in my rib is 2. So I'm missing out on 2 additional load balancing options for ECMP. And ECMP here is redundant. When you go and configure this, you can do a max pass 2 and question mark it out. And you'll see that by default, it's a much higher number. So maybe if you wanted to limit ECMP, you could push this down. Our recommended practice is just to have it equal whatever our max path is. So spine equals 6, max path equals max path to 6, ECMP 6. Next, you'll notice a BGP listen statement. And this is just a functionality that we can use only on one side of our BGP peering. Obviously, because if we set it to listen, if both sides are listening, it's a lot like LACP. If both sides are on passive, nothing's going to happen. Someone has to start our TCP connection. But it makes sense to set this on our spines because we're going to have a lot more leafs. And when we do this, we can dynamically listen for TCP handshakes using a range. So we can put all of our leaf switches in this range. And we'll assign it to our peer group. Here it's for our overlay, but we also have a separate peer group for our underlay. And we're going to add some security using a peer filter. So we are going to filter on this prefix list of leaf range and only listen and accept TCP connection requests for particular ASNs. So this leaf range will be our ASs. This will be our range for our leaf. So if someone tried to hack in and they were outside of these parameters, we would not actually listen to them. These are going to be our loopback 0 IPs. Our underlay, we're using directly connected L3 interfaces. So we'll set up a listen range for our underlay. Again, adding the security of our specific AS numbers. And then if we start with our overlay peer group, what attributes are we going to put on all of our neighbors that are in our overlay peer group? We're going to be using our loopback 0 as our source. Since we're going from loopback to L3 connected to L3 connected to loopback, we want to set eBGP multi-hop to 3 for all of our neighbors. We're also going to make sure we include send community. Here we've specified extended. Typically, we would just use send community. The send community keyword includes extended and standard communities. So by default, simply send community will send those. And we want to send both. If you add the extended keyword, it's only going to send the extended community. It does not send the standard community. And you might recall from the BGP class that the standard community is where the G-shut field is located. And the G-shut field is what we use in maintenance mode to drain a switch of traffic. And when we send that standard community, it has the G-shut field or flag, which tells us to set our local preference to 0. So it's just going to be a little bit of a BGP convergence while we route our traffic away from the device that is no longer locally preferred and send it to our device that has a local pref of 100. So if we use this, then what it does is we no longer can use maintenance mode on this device. So just set it to send community. And if a customer asks why, you can tell them that by default, this keyword sends both standard and extended. We're going to set our max routes to 0. Why would we do this? Well, this is our control plane. And we do not want to miss control plane packets. So when you set it to max routes of 0, we're saying there is no maximum number of routes we can accept. For our underlay, it's a little bit different. We just leave it at the default of 12,000. Will we hit 12,000 routes for the underlay? Probably not, but if you wanted to, you can tweak this knob. Because if you do go over your max routes, then it'll reset the session or it'll shut the neighbor down. Now I'm trying to remember, but you can make it so if you do go over the routes, it'll just send you a warning and it won't actually impact your peer group. Here we're also sending both extended and standard communities. And then finally, for this section, we're going to redistribute our connected routes. And here we have created a route map called loopback. And we want to redistribute our loopbacks. Why? Because we need L3 connectivity in our underlay for all of our loopbacks for both EVPN and VXLAN. So we're going to redistribute those into our underlay and into BGP. Next, you'll see that we have 2 address families that we've specified. There are many others that we could use. First, we're going to specify our EVPN address family, setting BGP for next hop unchanged. So this guy would be a configuration, as we already know, on our spine. We would not have this set on our leaf. And then what peer group are we activating? We're activating all of our neighbors in the overlay leaf sessions peer group. And then for our IPv4 unicast address family, we're going to activate the underlay leaf sessions peer group. So this is our basic, super basic configuration for just the underlay and the overlay using eBGP. Sorry about that. What was the last thing you guys could hear? Hello?
Hello?
You hear me?
Yeah, we're just discussing this configuration of spine.
Okay, so the last thing you heard was we were pretty much done.
Yeah, we're pretty much done with spine layer configuration.
And remember, our neighbor statements are part of this listen range. It will look different on our leaf, which let's see if we have one. Yep, we do. Okay, so this was our spine.
The screen share is gone.
Oh, thank you. That would be helpful. Okay, how are we looking now?
Yeah, it's good. We can see it.
All right, so this was our base configuration for our spines. Now let's take a look at some of the differences that you would see for our leaf switches. So again, we're gonna turn on our BGP process, assign it an AS, use our loopback 0 as our router ID, turn off our old gate D configuration, set our max paths, and then we'll create our overlay peer group using our remote AS as our spines. Remember, we didn't have to do this with the spines because we were setting it here with our listen statement. So we set it as our spines, which is 65,000, our update source. So who our EVPN peer will use as our source. Again, eBGP multi-hop is 3. We just want to use send community, max routes of 0 for our control plane. We don't want to turn any control plane down. For our underlay, again, using our remote AS, default max routes of 12,000. And then because we're not using the listen command, we have to explicitly configure all of our neighbors. So for the underlay, we have two neighbors, so two spines in our underlay. And then we'll have two neighbor statements using the loopback 0 IP and associating that with the peer group of our overlay. This next statement, you might can guess, is our MLAG peer. Next top self, and we're going to redistribute connected. On our leaves, we're only going to have this one statement to activate our overlay neighbors. And in our IPv4 address family, we're going to activate the underlay peer group, as well as our peer, our MLAG peer. So a couple of differences between the spine configuration, which is acting as a transit. So we want these spines to be invisible as far as we're concerned with the actual routes that are being sent between the leaves. And then with the leaf, if we're running MLive, we're going to have some additional configuration. Any questions with the leaf and spine base configuration?
So this maximum pass 2 means we usually don't have like no more than 2 spines, right?
That's what it means in this case. You will set this number typically to however many spines you have. So it would be a 4, indicating we have 4 spines. I mean, that's not telling us we for sure have 4 spines. But if we have 4 spines, why would I not take advantage of having 4 equal cost paths?
Is it like common, like having more than 2 spines in real practical deployment? Or
I've seen 4. Has anyone else seen any? I almost want to say that 4 is what I am accustomed to seeing, but I haven't taken cases in a long time, and I've only helped on a couple, and the ones that I've helped on are usually 2 to 4.
Okay.
Ken, have you seen anything? What do you typically see in professional services? I'm breaking it. I'm going to try switching my VPN. Okay, I just changed my VPN. Hopefully that helps. Ken, I don't know if you heard me, but have you seen anything else in professional services with customers that go above 4 spines? Hello?
I think we can hear you, but probably can.
Ken might have stepped
cannot.
away, but
Yeah.
Anton, you could hear me?
Yeah, I can hear you.
Okay, so maybe Ken just stepped away. I know he's working on his ASL3, but keep an eye on it. If you guys see something crazy like 12 or 20, let me know so I can share it for the next class. But to answer your question, I would expect that we would want to take advantage of all the spines that we have for our equal cost of having. I think that.
So, Sarah, just to confirm on a high level, the role of spine is to provide this VTEP to VTEP connectivity and also the ECMP path, for all the VTEPs, right?
It's correct. It's an aggregation point for all of your VTEPs.
Mhm.
And if you're using the traditional use case is eBGP with spines serving as transit routers or route servers, where they are just an invisible piece to the EVPN domain and serving
Right.
as an aggregation point for all of your leaves.
right? For that, we just want them to have accommodate the required MTU requirements, and also the not to interfere with the any of the extended communities being exchanged between the VTEPs, just to relay them across to the VTEPs, which it is receiving from another VTEP.
Right, they are doing normal BGP things, and then they are sending and receiving all of the EVPN route updates,
Sure, sure. Thank you.
but they're not participating in the data plane at all.
Okay. In case, when there are cases when we also have VTEPs configured on the spine, in that case, I think it would be decapsulating the VXLAN encapsulated packet and looking into the inner packet details as well.
Yeah, if it's acting as a VTEP, it's gonna do all normal VTEP stuff.
Okay.
So it does get confusing when they're using the term spine, but then the spine is actually just another pair of VTEPs.
VTEP.
And then usually we're just troubleshooting the VXLAN portion, or not the quote unquote spine. So if they have other services or devices off of the spine, or they're using IBGP, it just gets weird because it's not a typical design architecture that we see. But yeah, if you have the VXLAN configured on it and it's acting as a VTEP, then just treat it as a normal VTEP and troubleshoot as we
Got it. Got it. No, thank you.
Of course, good questions. I think these just walk through everything that we've already gone through. So IBGP does have different configuration. If you guys want to play around with IBGP. All right, design considerations when picking your autonomous system number. Just for the sake of time, I'm going to go ahead and skip it. I know professional services goes in one direction for it, but most of the cases that I see, they're still using the older ASN notation where it's just like a 65,000 number. And then do you have all of your leafs in different ASs, or do you just use one AS number for all of them? Most of the time I see the design choice on the left. If you use the design choice on the right, just keep in mind that you need to use this allow AS in for loop prevention, which basically means that if I'm going to have this 65,001 on my path, when this remote leaf receives it, typically he would drop this route because he sees the 65,001 and he's like, well, I'm 65,001, but we don't want him to drop it. But again, the design on the left is what I see most of the time. If you do see something like this, just be aware that you'll have to take some other steps just to make sure there's nothing wonky going on. We haven't talked about it, but in MI, you don't want to use the same loopback for VXLAN and EVPN. I know in everything you've seen, we have not used it. But just make sure that the customer also is not using the same loopback. I've never run into that myself.
Is that the VVTEP IP you're talking about in case of a EVPN environment?
No, so the virtual VTEP is a feature that we use that fixes a lot of the limitations and issues that arise when you have redundant gateways. When you have redundant gateways, then you're gonna have multiple ARP replies. For example, when you have a host, ARP versus Anycast gateway. Well, that ARP is gonna get flooded across your entire VXLAN domain, which means every VTEP is gonna receive a copy of it. Every VTEP is gonna see, hey, this is an ARP request for me. And every VTEP will reply. And then next thing you know, that one host is going to be getting all of these ARP replies from all of these VTEPs across the domain, and you're going to see ARP flapping, where the router MAC is going to change. Or you're going to see flapping between the virtual MAC and the router MAC. So that's just one example. There are a few things that come up just by nature having redundant gateways and broadcast traffic and unknown unicast traffic. So the virtual VTEP IP, which is the secondary IP that gets configured, when you turn it on, it changes the behavior of ARP. Because really it's ARP that causes the majority of the issues. And what it's going to do is there's a set of rules, which we're not going to go through here. If you guys would like to have a dedicated virtual VTEP class, I'm happy to give that to you. But it changes the rules of ARP, and it changes the rules of how we populate headers using the virtual MAC versus the router MAC, which solves all of the problems that come up just by nature of having an Anycast IP.
Got it.
The long
Can we
story
use
short, that's what the VTEP IP is, and you would use it in VXLAN. When you're using EVPN as your control plane, you don't need to worry about that because ARP suppression takes care of all those.
Right.
The only time you need to use virtual VTEP with EVPN is if we're using EVPN on a stick. So if we have centralized EVPN where we're only running EVPN on like one set of routers, then you're going to need to use virtual VTEP. I've never actually seen anyone but one customer use a centralized EVPN, and I'm not sure if they still are.
Got it. Can we use a peer routable MAC feature in case we are using the virtual VTEP?
Ask that question again. I don't quite understand.
The peer routable MAC. I think I don't clearly remember what the use was. I think it was using the same MAC address, like you said, there would the difference in the virtual MAC and the router MAC across the peers, and they both using the same VTEP IP. It may cause issues. So can we use probably a peer routable MAC or a common MAC so that we don't see that MAC flapping happening quite a lot, or we don't see the MAC flapping happening at all, and we could save on some address family like IP addressing as well.
So I'm not quite sure. You'll have to get back to me with the exact command you're thinking of. The only one
Sure.
that I can think of off the top of my head is when we have MLAG. And traditionally we would send the unique router MAC with our responses, but you can set it to a shared MAC, which is then sent out, and that's a command underneath the VXLAN interface. And it might actually be in these slides. It probably is in these slides farther on, and I'll look for that to send out. But when you turn on the, and I don't know if it is VXLAN shared router MAC or VXLAN MLAG shared router, or it's something along those lines. But when you have that turned on, then we use the MLAG system MAC that gets created when MLAG is configured. And we use that system MAC as our router MAC on both peers. So when a response gets sent to the MLAG, regardless of which peer it hits, both of them have the ability to process that packet versus having to send, say I'm peer 1 and I get a response that has the router MAC for peer 2. I would have to send it across my peer link. And it wasn't, there was nothing wrong with that. It was just suboptimal. And now with the shared router MAC, either one can process it and we don't lose that extra hop every now and again when it hashes to peer one.
Got it. Got it.
There's
I think I
another
just,
shared
have the-
router MAC that there's actually two commands, but I think the one you're talking about is the shared router MAC for the NLAG. I'm gonna have to look up what the other one I'm thinking of is.
Yeah, we could probably sync up after often.
Sounds good. And then I'll send it out to all of you, just for clarification. But the MLAG shared router MAC is for that use case. All right, so there's a couple of slides here, which, all right, update, wait, install, and wait for convergence are two additional knobs that you will traditionally see under your router BGP configuration. And this is, do not install routes until we finish converging. It's just gonna add a little bit of time, make sure BGP is stable before you start saying, okay, this route is available. It just gives us more time because otherwise you can block the traffic. All right, so that was the base configuration. That is just establishing your infrastructure, your underlay infrastructure and your overlay infrastructure, and then turning on your address families. That's your base configuration, which when troubleshooting EVPN are going to be the first things you're going to check. And those are really easy to check. Show IP BGP summary for your underlay and show BGP EVPN summary for your overlay, which we will may or may not have time to show you today, but whatever I don't have time to show you today, we will definitely start tomorrow off with. Now that we have our base infrastructure, what else do we need to configure? And this is where I like to think of our constructs. At I think of 6 constructs. We've got our layer 2 construct, which is our VLANs. If we don't have VLANs then configured, then we can have everything else configured, but we're not actually using any resources, not until that VLAN is configured. Our L3 construct is the SVI. And then we have our data plane constructs, which is everything under VXLAN. So our L2 VNIs and our L3 VNIs. And then we have our EVPN control plane constructs, which are our L2 VPNs, aka our MACverse, and our L3 VPNs, aka our IPverse. So I simplify EVPN down to those 6 things. And if something is broken and it's a new configuration, it's never worked, then once I have confirmed my base infrastructure for my underlay and my overlay, that's the next thing I'm going to check. Do I have my L2 VPN and L3 VPN set up correctly once I know what he's trying to accomplish? Because I might not need an L3 VPN if I'm just running asymmetric or L2 VPN. And then on my VXLAN, my data plane, do I have my L2 VNI configured and my L3 VNI configured correctly, depending on which ones I need? And then do I have proper L2 VLANs and L3 SVIs set up if I'm using layer 3 routing? So those are the 6 pieces on top of the base infrastructure that I simplify it down to. So here, we've already covered that there are 2 different types of MACverse we can be running. That L2 VPN with IRB, that just means a usual MACverse, but then I'm also using IPverse, because when I'm running IPverse, then that will change things a little bit, which I'll talk about when we get to that section. Quick note on if we are using a leaf pair as a border leaf. and its functionality is connecting data centers or connecting to a campus or to cloud services, then we're going to use the command remove private AS, because we don't want to have private ASNs appended to our AS path, because we're going out to the internet or we're going out where there isn't that level of security. And then if we are running firewalls, we're going to need to use NAT. See if we have a configuration example here. No. I'll let you guys play around with these path selection slides. Talk about that. Okay, this is just a side note slide with route distinguishers. We've already talked about how you would want the route distinguisher to be unique. This is good for redundancy, and it's just also good for troubleshooting, that you know what to expect. And if you're not getting it from one of the leaves, which actually, funnily enough, was the problem with that IBGP customer. One leaf was good and one leaf was bad. And you could tell that with the route distinguishers, because we weren't receiving routes. And if we had used a shared route distinguisher, then that would have been more difficult to see as quickly as we saw it. When using shared router MAC, which is what Madhukar and I were discussing, there is no need to configure a unique RD per VTEP. I would still use a unique RD just for troubleshooting. It is going to save a lot of time. So I would, just based on my experience, yes, you have fewer routes overall because you would install that. So if you are having a scale issue, maybe then you don't use a unique route distinguisher for each peer. But if you don't have that many routes, then I would use a unique route distinguisher for troubleshooting purposes. So depending on a customer's environment. And then when you are troubleshooting a customer's environment and they're running MLAG, make sure you find out, are they using unique RDs or are they using a shared one, just so you know what to expect on the far end and you're taking a look at what routes have been received. So this is what our lab is for today, and probably carrying over into tomorrow. It's just doing a really basic layer 2 VPN. We're going to be just bridging between VLAN 10 and VLAN 30, which is just typical VXLAN bridging. But again, we're exchanging control plane state, aka our host MAC information, via these type 2 routes in EVPN. We're also going to be exchanging type 3 routes to build out our flood list. Nothing changes. Data plane forwarding is always going to be VXLAN unless we're using MPLS, which this class isn't about. Do not turn on any SVIs. This is pure L2 for the first lab. Feel free to use a VLAN-based MacBerth or a VLAN aware bundle. Feel free to do both and look at the differences in what the packets look like. Just remember that you can't cross them. Okay, so this actually has, where is this one? All right, let's walk through this. If I'm a host in VLAN 200 in green over here on the left, and actually even before we start talking about hosts in this bridge domain, let's talk about what happens when we configure this on my switch 1 VTEP. As soon as I configure this, I'm going to start advertising the type 3 IMET routes to switch 2 and switch 3. They also have EVI, which is our EVPN instance or our MAC version of 200. So when they receive this type 3, and assuming that our route targets are correct, then they are going to add switch 1 to their flood list. And the same thing, switch 3 will add switch 2 will add switch 3, and switch 1 will add 2 and 3 to its flood list. And this happens once everything is configured correctly. So let's make sense of what we're looking at here. We have this server 22 who wants to reach out and talk to server 23. Server 23 is on remote VTEP 2. So what is this going to look like using EVPN in the control plane? So when server 22 first pings server 23 at 2223, and notice that we are in the same VLAN 200, so we don't need to worry about any sort of routing. We are going to hit our local VTEP. And I'm trying to figure out if we've already, yeah, all right. So we've already learned everything. Server 23 has already been speaking to his VTEP 2, which means VTEP 2 has sent out type 2 routes to all VTEPs in its flood list. VTEP 1 was one of those. So VTEP 1 knows about host server 23. So when server 22 pings him with a source MAC of himself, looks like he already knows his destination MAC, but maybe he, all right, this looks like a super simple packet log. All right, server 22 already has all the information. He's got the destination MAC to server 23. We already know the IP because we entered it ourselves. So as soon as this frame hits VTEP 1, we're going to do a lookup in our local bridge table for VLAN 200 for this MAC for server 23. We already know it because we've learned it, and we know that server 23 is accessible through this VTEP 10201 with this L2VPN 200. We will encapsulate this packet frame, whatever you want to call it, with our outer header, which includes our outer destination MAC, which is going to be the router MAC for switch 2. The source MAC is the router MAC for switch 1. And I'm sorry, I will go ahead and say it is a personal pet peeve of mine when we can't order the header correctly. Because I think it makes much more sense and helps us in our learning to order the header properly in the correct order of the header itself. So we know that the actual outermost header is going to be our destination MAC, followed by the source MAC, followed by the source IP, followed by the destination IP. Anyhow, that's my own personal pet peeve, But the DMAC should always be first, because it also helps you think what's going to happen stack wise. Anyhow, we've got our outer header, which has been populated because of control plane state learned through EVPN. And then we have our VXLAN header with our VNI. And this is just a layer 2 VNI, so our L2 VNI. And then our unchanged inner header with our ICMP data or whatever traffic we're sending. It's a pain, so ICMP. We're going to cross our layer 3 underlay. It's going to go hop by hop, depending on how many routers we have there. Always doing a rewrite for our Ethernet header while doing a lookup for our destination IP. We will eventually get to our remote VTEP2, who will have a destination map of itself, its router map, so he knows it's for him. Then we see that outer destination IP is for him. He'll strip that off. Next thing is the VNI. We'll do the reverse with VNI to VLAN mapping to get into, oh, sorry, that would be a VXLAN block. When we do this, when we do our reverse VNI to VLAN mapping, we are actually going to be put into our MAC first using our route target information. So once that's how we know this information is here. This process would break if something had been messed up with our route target. But because we've already established that control plane state, that's all good. So with this L2 VNI, it's going to bring us into our local MAC birth and our local L2 bridging information and a bridge table. We will then proceed as normal. So it's very normal VXLAN, except that we are using EVPN to develop our control plane state. I'm actually deciding that this is not my favorite way to present all this, because just keep in mind that EVPN is building out your control plane state. All the steps that you learned in VXLAN is the same thing. And once the control plane state is established, then this path of packet is normal VXLAN data plane forwarding. But if we don't have control plane state, and when you do the lab, the L2VPN lab, and you will be establishing state for the first time, that's the homework I want you guys to do. Is step 1 of the homework is to build a pure L2 environment with VXLAN as your forwarding plane and EVPN as your control plane. I do not mind if you guys work together just to make sure you have connectivity. You might not need to, because it shouldn't be too hard. But then what I want you guys to try to figure out on your own, the second part, is to do a packet walk similar to this, but in this packet walk, everything is already established. I want you guys to write out what commands you're going to run, what happens when it's all brand new information. So for example, if I was going to start my packet walk here, and I'm just establishing my control plane, so server 22 is going to talk to VTEP1 for the first time. Then I'm going to do a show MAC and make sure that I'm learning about my host. I know that I know based on my MAC, because I'm using EVPN, that as soon as switch 1 learns about server 2, he's going to trigger the generation of a type 2 route. So then I want to run a command to confirm that that type 2 route was sent out. So So that's what I want to get to. And then I want to make sure we do that first before giving that part to you for homework. All right, let's talk about the configuration. Very simple. We have our layer 2 construct, so whatever VLANs we're going to choose. And then under our router BGP process and under our basic configuration that we've already talked about, we're going to configure our MAC verbs. These MAC verbs are VLAN specific, so just plain VLAN MAC verbs. You guys can choose to do a VLAN aware bundle if you wish. You have our route distinguisher, our route target, our redistribute learn. Notice our route target is identical on all of our leaves. And then we have one set up for VLAN 15. So this being our control plane state, as routes are exchanged, if they match the criteria for importing into our control plane, and leaf 1, 2 receives a route type 2 from a host off of leaf 3 and 4, and my route target is good, then I will import that into my VXLAN address table and into my MAC address table. And then, so this is my L2VPN construct. And then this is my L2VNI construct. So here's my data plane where I map my VLANs to my VNIs. And here's my control plane state where I set out my rules for how I'm going to build it out. So for a pure L2 VPN setup, then I only need my L2 construct, my L2 VPN constructs, and my L2 VNI constructs. So only half of them for L2 VPN. Okay. So now let's go through, we've got like 15 minutes. And just a quick for my topology. If you guys will go to the DC New Hire resources and click on the lab for today, you'll see something very similar. I've shut down my spine 2, so we can just use spine 1. And I've got a standalone leaf. No, MLI. And then I do have leaf 2 and leaf 3 set up. Let me close out these guys. For some reason. My spine is serving as just a transit server or a route server. And if I look at my infrastructure, I can see that my underlay to leaf 1 is good. And that my underlay to leaf 2 and 3 is also good. If I look at my EVPN overlay, I can see that my EVPN peering for leaf 1 is good, but I haven't received any prefixes. I can also see that my peering to leaf 2 and 3 is good, and I am receiving prefixes. If I go to leaf 2, I am active and connected. I'm also the secondary in my MLAG peering. Everything is already configured on leaf 2 and leaf 3 for my L2 VPN. And also for leaf 2 and leaf 3, everything is good as far as my overlay, my MLAG underlay, my BGP underlay, my address families, and my macros. What is not configured yet, if I look here, I know that my BGP is, I know my underlay BGP is good. So this is where I usually start with troubleshooting. Just a quick, is there anything funny going on here? I do have a neighbor to spine 1 and I'm receiving prefixes. However, I'm not quite sure why this is showing established. Something's changed. It was down. I shut spine 2 down, I thought. But in any case, I shut it down just because we want to do some packet captures. And I've got everything set up on spine 1. What do I have anything else configured? So I don't have any VLANs 10 and 30, which are just simple examples we've been using throughout our training to keep that part simple while we focus on the feature or the technology. So I'm not using up any resources here. I do a show run interface VXLAN. I can see it's only the bare bones configured. I don't have any L2 VNI configured. And the same with my BGP process. I just have the infrastructure set up, which is why I know that my underlay is good and solid. My overlay looks good, but I'm not actually sending any sort of traffic. If I look at my MAC address table, I don't have any entries. I'm also not learning anything in my data plane, in my VXLAN fabric. So let's go ahead and we have 8 minutes. Well, I do want you guys to play around with this. So let's see what I need. We'll just do it for VLAN 10. Let me make sure my host is working. So if I were to ping, this guy still hasn't come up, that's not good. Might have to hack something here if this guy is not coming up. Maybe I have spine 2 to be my host. Well, let me just go ahead and show you what should happen, because I know in your virtual environment, you won't have this issue. So if, I think it's 10, 10, 10, 30, right? Just confirm. Oh, maybe it's he's 101 or 103. All right, so ping 10, 10, 10, 10.103. All right, so I cannot ping my remote host, which he's down. So I would, but I don't have anything configured, so I wouldn't have been able to ping him anyways. However, what I should now have done is some local MAC learning on my Leaf 1 VTEP. Oh, that's not good. Why don't I, why not? Oh, duh. Now I feel so. Before I even attempt a ping, which clearly it's failing, but it's failing for other reasons. Like I don't have the VLAN configured on this box yet. So let's go ahead and walk through what you would need to configure. I need my L2 construct. Easy enough. Done. There are implications because that are cool to see that you can configure your VXLAN information. You can configure your EVPN information, but at zero cost to your switch. It's only once you configure your actual VLAN that you start to have a resource cost on your box. So you can configure your control plane and even your VXLAN data, but they're to no cost. So if you did a range, then say I did VLAN 10 through 1,000, I wouldn't be using up all those resources until I started adding those VLANs. So from a design perspective, that's kind of cool because I could have all of my VXLAN and EVPN configuration done and then only add VLANs as necessary. And that's for the same cost. So that's kind of cool. But moving on with this in the interest of that I have 4 minutes left. So I want to go ahead and configure my L2VNI. So I'm going to say VXLAN VLAN 10, and I'm going to map it to 10,010, say. So if I look at my configuration, now I have my L2VNI. So L2 construct check, L2VNI construct check. The next thing I need to do is my L2VPN construct, aka my MacBird. So I can come in here and I know that there's nothing configured. I want to do VLAN 10. There's my MacBird, my simple MacBird, VLAN based. I need to give it an RD. Loopback 0 is this guy, so I can do RD is 1.1.1.101. Say it's for VLAN 10. I could use VNI 10,010, doesn't matter. But as long as I know that any routes coming from VTEP1 are going to be identified with this route distinguisher, that gives me a lot of information. I know it's VLAN 10, and I know it's leaf 1. I need a route target. So with my route target, I can either specify individually or I have this fancy keyword. I'll go ahead and do that. For my route target, maybe I want to use the VNI itself. And then I want to redistribute any learned MAC addresses into BGP because I want to share this control plane state with everyone else in my EVPN domain. And that's it. I can exit out of there, run a show active, and there's my L2VPN, aka my MacBird. Let's see if I have any kind of state right now, or if I have to do another failed ping. Now that I actually have, okay, now that I actually have a VLAN, you'll see I'll start to have information. So I'm running this 0DBD, which should be host A. And it is. So I've learned, this is my basic, nothing special local MAC learning. As soon as I learned it, I will have triggered the generation of a type 2 route. And this is the command that you will quickly memorize, show BGP EVPN route type, because you're going to use it all the time. It's like looking at advertised and received routes in BGP. It's great, it's full of information, and it's going to be something you use all the time. You'll notice that on this version, I only have the 5 choices. I'm not using multi-homing, so I don't need type 1s, and I don't need type 4s. I am interested in type 3s and type 2s for my L2VPN lab. So let's take a look at my type 2. I could just hit enter here, and you'll see that I have a type 2 route here. but this doesn't give me a whole lot of information. So it's always more interesting to add the detailed keyword. When you have a lot of routes, you're going to want to get more granular. And you can do that by using the the IP address. Where's my MAC? There's my MAC address. Using the RD, if you want to look at what routes I'm learning from a particular VTEP. If I want to be even more granular, I can use the VNI. Oh, darn. Gosh. I wonder how long my carpool kids can wait before I put them. Let me just finish this real quick. If we add the MAC, so say we just want to grab the MAC and detail, then we will spend the start of next class here going through the information that we see. Right now, I just have a locally originated type 2 route, where as soon as I learned this MAC here, EVPN kicked in and created this type 2 route, tagging it on export with this route target 10,010, 10,010, as well tagging it with my L2VPN 10,010. Notice that it's a MAC only type 2. Also notice that I'm appending it, my route, with my route distinguisher. So if I grab this command and copy it, I can go to my remote VTEP and run it. And notice that I've received it on the remote VTEP. My path is through spine 1, and there's only one available because I shut down spine 2. If I have 4 spines, I'm going to have 4 paths available here. And it's all the same information, except now I've got my VTEP IP information. So 2221 is VTEP 1, leaf 1. I'm learning it though from my EVPN peer of spine 1. I have a route target of 10,010, 10,010, which if we look here, that would have been neat if it worked, but it didn't work. That I have this with route target 10,010, 10,010, which means that when I receive, when I receive this route, this is just telling me that I received the route. This doesn't actually tell me whether or not I'm installing it into my tables, but I should, because the route target looks good. And it should be in my MAC for VLAN 10 because of my L2VPN. So if I do a show VXLAN address table, I should have imported it. And in fact, I did. And you can see here that I'm learning about host A via EVPN, not via VXLAN, but through my VXLAN interface. And I know that I have to use VTEP 2221 in my outer IP header to reach this host. I also see it in my MAC address table that I learned it dynamically through VXLAN. But just remember path at packet, that on the return path, I'll hit my local MAC, my local L2 table, which tells me I learned it across VXLAN. I'll then come to my VXLAN table and say, okay, the information I need is this information. And also this information, because I'll need to map it to my L2VPN. All right, I'm going to have to stop here. I do think you guys have more than enough for the L2VPN lab. You saw how simple it is to set up, even if my hosts are messing up right now. And then remember this command. Show BGP EVPN route type. Before we leave, there's one last thing I want to share with you guys, and that is the troubleshooting EVPN, and you can walk through this. So if you don't already have this, I threw it in chat. I want you all to holler at me once you have it. And you can use this as a way to look at what commands to run. So I want you guys to take a look at show BGP EVPN instance. The show BGP EVPN. Oh, sorry, this is just what's in the extended EVPN. This will literally walk you through what you need to check. So I want you to start at the top, work your way down. If you have any questions with building out your L2 VPN, but everything in here is everything we've already covered. You already know the VXLAN piece. I go through again the constructs. Go ahead, Gani.
We need to like build a lab from scratch, or we need to build it like based on this.
So this is the lab that you should have hooked up with, and what I would do is clone it from what you did, because it's the same exact lab as what you did for the VXLAN piece. You may or may not need to add some hosts, but really I'm just testing you. I'm just having you guys run through L2 VPN. So you really just need host 1 and host 3.
But the cloning doesn't actually save the configurations for the new one, right?
It does if you're on VIOS console, but I know most of you are on Eve, and yes, there are cloning issues with Eve, but you can still clone it and then copy paste. Annoying, I know, but once you've done whatever you want to do, you just have to build the structure for your overlay for EVPN. So you will have to do your router BGP for your overlay, and then you'll need to add whatever construct is missing. You will most likely, if you clone and copy paste, you will already have your L2 VNI. You will already have your L2, which is the VLAN. The only thing you won't have is your L2 VPN construct, which is the macro.
Okay, VTEP 2 and 3 is MLAC peers, right?
Correct.
Okay, so task for
You
today
can
is
play around with that shared router map that we were talking about earlier.
Okay.
But between these two, I think you guys should be good to go. And what we'll do tomorrow is we'll start by walking through the path of packet and taking some packet captures, looking at the type 3, looking at the type 2, and then we'll talk about IRB. I do have to run. If you guys have questions, would you please email them to me? Because if you have questions, probably someone else does. And I'll start off so we have them on the recording with any questions that we can share with everyone. So thank you guys so much. I apologize for having to run. I will share the recording. Let me go ahead and stop it once it's finished converting.